Hi, welcome to the Calculus 3 lecture series. And from this video, we're going to start a new unit. And this unit is multiple integrals. So basically, we're going to take a look at how do we do the integration if I have more than one variables. So our first lecture, lecture number 1, is let's take a look from the basic, how do I do double integrals of the rectangles. That means how do I do double integrals and over the regions of the rectangles. Okay, so now let's go ahead and take a look at what type of the problems we are going to have here. Okay, so before we start, let's take a look. Okay, so let me do a brief review about what we did in the calculus 2s, right? So let's kind of do a brief review, then we can see what is the calculus 3 we have. So this is, we start at calc 2 when we talk about the integration. So when we talk about the definite integrals here, that means when I take the integration, I have the upper bound and the lower bound, the f of x dx here, right? So in the calc 2, so we said first, we say what is the meaning of these ones here? So basically, this is what we talk about when we do the integrations here with the definite integral with the low and the low upper bounds here. So that means over these intervals here, right? If this is my function, and this function is f of x here. So when we talk about, like when we try to take the integrations under this function between in this interval, so what are we doing here? Basically, we are trying to calculate what? We are trying to calculate the areas, right? So we are trying to calculate this area under this curve, and then we'll try to find the area. Okay, so now you say, how do we find the areas here? So, so in the R2s, right? So this is the R2. So the definite interval, what do we here? We are finding the areas, right? Okay, so like also then we learn how do we find the areas here. So for examples here, right, let's take a look. Let's start with the same function here. So we say this is my functions here. That's one, don't like this. Okay, so let's say here, this is more dramatic, right? So this is my functions here. So I have A and B. In order to find the area, so what we did here, we say, hey, let's divide this interval into several sub-intervals here, right? So for examples here, let's try to do here, I'm just divided this interval to 4 sub-intervals here, right? So for each sub-intervals, and then I can find a rectangle. So for here, for example, I'm using the left-hand side rule. I can find the rectangle by using the left-hand end pointer, right? So here, and here, and here, right? So now, by using the left-hand rule, so I can say, okay, this is my first rectangle, and this is my second rectangle, and this is my third rectangle, and this is my fourth rectangles, right? So now we say, okay, so for each one here, the sub-interval is delta x, right? So how do we find the delta x here? In general, it will just be your upper bound minus lower bound, and divide by x. Here, so how many intervals here? And then in here, depend on your rule. Like for here, I use the left hand rule. So I find I use the left hand, try to find the height, right? So I use this height. So I have the width and the height, so I can find the area of each rectangle. Then I add them up together. Then we say this is we say when the time we are kind of divided the integral into the many sub-intervals, and then you know, the area of the integral going to be very, very close to two areas. Okay, so we say, okay, so this is what we say. Okay, so here then we say we can summations, right? So we say the f of xi star and the times delta x here, right? I is from 1 to n. So this is the height, right? So this is the height for each subintegrals here, right? So this is the height and this is the width, right? So that's why I said the height times width will give me the, the area of those rectangles. So what do we call this? If you still remember in the calculus 2, we call this here what is the what? We call this is the Riemann sums, right? So we call this is the Riemann sum of Riemann sum of this integration. So then we can write this one here. We say AB f of x dx here will just be equal to, when you have a limit n approach to I think n approach to infinity, then you have I from 1 to n, f of xi star and the delta x, right? Delta xi is here. So, okay, so that means now if you divide this interval to many subintervals, then the area of the sum of all these rectangles will be very, very similar. We're very close or approach to the true area under the curves, right? So now, now in the Calc 3 here, we have the same things here, right? So now let's take a look in the R3s here, right? So what is like in R3, because here this is the, right? So this is X, Y, and Z, right? So if you have some function, so right now I know in R3 it's not, so we have some type of the surface like this in R3. And then what happens to my integration area? So that's what is this topic we're going to talk about. So let's say that in the integration area, I have some rectangle integration areas here. Okay, that means X is from, from the A to B, and the Y is from the C to D. So I'm integrating this, this functions over, so these functions here is f of x, y here, right? So that means I am integrating these functions over this region. So what's that means here? That means in here you have f of x, y, right? So then you say, okay, now I have a dx, dy, then the x here is from A to B and y is from C to D here. So that means I'm integrating over this rectangle area. That's what is the title for this first sections, right? So what do we are trying to do here? That means in here, I don't know I can really graph this good or not. Okay, so instead of, you can kind of see it, right? So instead of the area, what I'm looking for here in the R3 here, I'm finding what? I'm finding the volumes, right? Okay, so I'm finding the volume, okay? So in here, the same ways here, the x, y is like here, like in the Calc 2, we said x star, so it depends on which points you want. So here is the same. So what is our Riemann sum going to be? So instead of each individual rectangle, so what I'm looking for here, I'm looking for the rectangular what? Presence, right? So it's kind of like a rectangle box. So I'm going to add all these smaller rectangles here. So basically, so you will have, this is the summations here, right? So you will have a xi, j star and yi, j star. Then you will have delta xi and the delta yj is here, right? So I is from 1 to n, j is from 1 to n here. So basically, you just divide. So the x-axis you can divide. So basically, so what is the delta xi here? That means is x-axis, right? So it's b minus a. It's very similar like algebra in the calculus too. So it's b minus a to the m intervals, right? So that means from the x-axis, I'm going to have m subintervals. And then for y's here is from the D to C, I'm going to have n subintervals. So the whole area I'm going to have like what the m times n subinterval, the little squares, right? So like a little each region, not necessary to be squared, each rectangular small region. So now in here, this is the one. So this is what? This is the base area, right? So the length times width. Then what is this ones here? This is the height of this rectangular prism, right? So that's why the same thing, we are using the rectangular box. And so if you add all these small boxes here, it will be very close to the integrations here, right? So the true volumes here, right? Okay, so that's why, that's what we're going to get the true volumes here. Okay, so now let's take a look here, the definitions here, right? So that's why we said here that this is the first ones here. We are talking about the integration region is a rectangle. Okay, so it's AB and CD. So X is from A to B, Y is from C to D. All right, and this is the easiest one. And the next section, we're going to talk about how about if you don't have a rectangular, integration region. So delta x is you divided by m, and the delta y is here is you divided by s here, right? So in here, the base area is delta x times delta y. Then here, this is the double Riemann sum, right? This is what we call it the double Riemann sums here, right? So it's just the height times what? Times the areas here. So that means if you cannot divide it into many, many subintervals here, then you let the m and the n both to infinity, it will, the volume going to be approach to your double integration, right? So this is the kind of the pictures here. So basically you are looking what? You are looking for this this volumes, right? So you are looking for these volumes, right, from this rectangle. So that's what is double integrations try to find is the volumes under that curve here. Okay, so now let's take a look. See here, the problem number 1 is here. They say let's try to find the Riemann sum and they use them. So let's see here, this one here, they want to use the left side midpoint. Okay, so left hand side midpoint. Okay, so now the first thing is here. Let's try to write it. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So here this is 9 and this is 10. So this is 1, 2, 3 and negative 1. So the first thing is let's graph where is the region is from 1 to 9 and negative 1 to 3. So basically this is my regions, right? So it's okay. So it's from the 1 to 9 and the negative 1 to 3. Then here they tell you x, I'm going to divide it into how many? 4 subintervals. So from the 9 to 1 is 8. So every subinterval going to be have 2 here. Okay, so this is x. I have the, so what is the delta x here? Delta x equal to 2, right? Okay, now the n going to divide by 2, n equal to 2, that means the y area I'm only going to divide by 2. So total is 4, so each one going to have 2, right? So this is my delta y, see here. So what is the delta y, see here? Delta y is 2 also. Okay, so now let's use the left-hand side midpoint. Left-hand side midpoint. So this is the first one, right? So this is the second one. This is the third midpoint. This is the third. So this is the midpoint. All right. So I'm going to use the, so you visualize this one. You're going to touch your functions, right? Have a height here. So let's mark here. So this is R11. This is R11 here. R11. This is R12. R23. So this is R21. So this is R33. And this is R31 here. And this is R42. This is R41 here. Okay, so after that, so basically you just try to put a table. This is kind of a little tedious, right? So this is Rij's here. So let's do few. So the R11s here, right? So what is your Xi star and the Yi star here? Okay, so the Ij is here. So because R11, so I'm looking for the midpoint, right? So what is the midpoint here? It's 1, 0. Then you plug in this Ij star and Yij star to your functions here, right? So you get a 5. Then you times this Xij star Yij star times the area. So because the area, delta area is delta x is 2, delta y is 2. So it's delta x times delta y. So what is here? Is a 4 here, right? So here, let's say, so 1 times 4, this is 4. Let's do a couple more. So let's take a look at R12 here. R12 will be this point, right? So x is equal to what? It's 1. So what is y? Y is equal to 2. Then you plug in your function, you will get a 5. And then here you will get a what? 20s, right? So you you do the, let's do the last ones here, R42 and R41s here, right? So let's do that. Okay, so let's take a look at the last ones here. This is R42. R42 is this point, right? So what is this? That's 7. Okay, 7 and the 2's here. Then you substitute to the functions. 7 is 49, so it's 53. And the 53 times 4 will give you 212. Okay, and now you just, then finally, you just add all these things together. So if you add, this is 736. So I know the Riemann sum is equal to what? 736. That means if I use this to estimate, it will be the 736. Okay, so now let's take a look. Let's say they use the middle point rule with m equal to 2. Okay, so with m equal to 2, that means x-axis I'm going to divide by 2, and n I'm going to divide by 3 here. So this one's here. So this is x, right? So this is x, this is y here. Okay, so let's take a look at delta x here. Delta x is what? 2 minus 1 divided by 2. So it's what? It's 0.5. And delta y here is 2 over 5. So it's 5 minus 2. And over how many? 3. So it's what? It's 1 here. So now my delta area will be delta x times delta y, right? So this will be 1/2. Right? So it's 0.5. Okay, so now you want to use the middle rules again. So let's take a look here. Okay, so this is the 1, 2, 3, 4. This is 1, 2, 3, 4, 5. Okay, so the x is from 1 and 2, right? So this is 1, 2. I need to divide it by half. So this is the, so the 1, 2 is here, and then the y is in here, right? Y is 2 to 5. So this is my, the integration area, right? It's 2 and this is 5. Because of, okay, so delta x is 0.5. So this will be my delta x divided, and then here is divided by 1. So how many sub-interval, sub-area I have? I have, you know, I have 6. So now in here, be careful, let's say use the midpoint, right? So what means the midpoint? So the midpoint here, that will be right in the middle here, right in the middle here, right in the middle here, right in the middle, right in the middle, right in the middle here. Okay, so now let's take a look at the Riemann sums here, right? So the same thing, let's try. Okay, so let's try to do the, so if you want us here, you can do a different table. So you can say this is xi. So here, so the Riemann sum, the first one is here. This is a 1.5, right? Okay, so the middle ones here, the first one here is 1.25. Then this is 1.5, then this is 1.75, and this is 2. That is the x values here, right? Now the y value, so it's middle, right? So this will be what? I have 2.5 through 2.5. No, it's 2.5. That's right. Okay, 2.5. So here, y will be 2.5, 3.5, and what? And 4.5. Y is from 2.5 here. I'm going to have 3 areas, right? Okay, so it's 2.5, 3.5, and 4.5 here. All right. Did I get that one correct here? Let me take a look. Okay, yes, I think I got it right. Okay, so now in here, you can use my table before. Some people, use this table. Then here, this will just be x equal to 1.25, y equal to 2.5. So you will have, this is 3.125, and then 1.25, 3.5, you get 4.375. Then this one will be 5.625. And then this one's here, x equal to 1.7. Oh, yeah, I know I get something not quite right here because m is 2. So the first one is 1.5. The second one is what? 1.75 here. Okay, got kind of confused here, 1.75. So I only have 6 regions here. So you plug it in. So this is a 4.375 and the 6.125, and this is a 7.875. Okay, and then you add all of them together here, right? So you add them together, and also then you times, so this will be the sum, right? So you can add them together. So then the Riemann sum will be, okay? So so if you add all these ones, it's 31.5. So the Riemann sum going to be when you add all the function values. So like in here, inside here, each one, this is a function value, right? Xij star, Yij stars here. So then the Riemann sums here will just be 31.5 times the delta A's, right? So the delta A is 0.5 here. So the Riemann sum will be 15.75 here. Okay, that's a pretty, it's just like a very routine and tedious work here. Okay, so now let's take a look here. So let's say estimate the x plus xy and the dA. Use middle rules with delta x and equal to 0.5 and delta y equal to 1 here. Okay, so in here, this is not very well written. So in here, it will, this one's here, that means I'm doing the dy first and the dx here. So this region is the value of the y, and this region is the value of the x. So you might want to change this to the dy dx here, okay? So now the dx is equal to 0.5, right? So the delta x is equal to 0.5. That means 0.5 is equal to, okay, 4 minus 2 divided by n equal to 0.5. So I know n is what? I need to divide it into 4 subregions of the x. Then the same way, the dy here is 1. That means 1 is equal to what? 1 is equal to 5 minus 1 divided by n. So what is my n's here? My n is 4. So that means I'm going to divide my area to 4 subintervals. So total, I'm going to have 16 kind of the areas, right? I need to add it up here. So let's see here. So we can do a very similar ones here. Okay, let's do this ones here. So we have a 16. So this is the 1, 2, 3, 4, 5. And this is 1, 2, 3, 4, 5. So x is from 2 to 4. Y is from 2 to 4 is here. Y is from 1 to 5. So it's in here. Okay, now I'm going to divide both into 4 areas. So y have 4 area, and then the x here also have 4 area. So as you can see, I have what? I have 16 subintervals here. Okay, now these ones here, they want the middle point. So still is in here, 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 here. Right, so all these are the middle points here. Okay, so this is what we call it the renaissance here. So this is 2, 3, 4. So this is 1, 2, 3, 4, 5. So we can find tables here. So we say the axis start with what? 2, right? So the start with 2. So the first point, this is 2.25. Then the next ones here is 2 point what is here is 2.75. Now I have 3.25 and I have what 3.75. So this will be my xij point. So the yij point is the vertical one. So first one I'm going to have 1.5. Now I'm going to have what 2.5. I'm going to have 3.5. I'm going to 4.5. Then you plug each numbers into the functions, right? So it's 1.5, 2.5. So you will get this ones here. So you will get this ones here is 7.125. And this ones here is 8.375. And so this one is here is 16.875 here. So it's very tedious. You might want to use like Excel or something to help you to do that. So after you input everything, so this one's here, 25.125. Okay, so then we're going to summation. We're going to add this all up, the sums, right? So we said the summations, J from the okay, so we have a j from the 1 to 4, I from the 1 to 4, right? Now we have f of xij and yij here. So if you add all this together, this will give you what? It will give you 240, okay? So if you give you 240, So what is my delta area? Delta area is delta x times delta y. So it's a 0.5. So what is here? So my Riemann sum is equal to what? 240 times 0.5. So it's 120. That will be my Riemann sums here. Okay, and so let's take a look next here. Okay, so let's continue. So like here is kind of like the summary what we just did here, right? So it tell you, and here, so here, that means here's the summary like we just did. Okay. So we know like if you have your, so this integration regions is a rectangular regions here. So basically you are looking for the volumes of the solid above R, right? So this is, we call this integration region. So like we, you know, a while ago we see this volumes here, all right? So here we have the few very interested property about the double integrals here. So let's say if you have two functions, if you add two functions and over this integration region, you can separate that. And so you minus, you can separate that, just like in the Calc 2, right? So in the Calc 2, if you have like AB, if you have fx plus gx or minus gx dx, right? And then you can separate that. So you can say AB f of x dx plus minus AB gx, right? dx. So this is in the Calc 2s here. We know we can do that. Now also in here we say, hey, if you have a constant, right? So if you have a constant here, you can move these constants out. We did that in the calculus 2 also. If you have a constants times the functions, you can do that. And also, let's say in here, they say, okay, if f of xy greater than gxy in all this, for all the value in this R is not real number. That means this is the integration regions, right? So that's what it means. This is regions here. Then that means when you do the integration, it will be greater. It's kind of like intuitively true, right? That means this one will have a bigger volume than this one. Okay, let's take a look at number 4 here. They say write a double integral to find the volume. Okay, so let's in here they just want you to, you know, to see here, right? So that means in here I'm writing the integrals here. Okay, so I'm trying to find the volume under this curve. So it's 12 plus xy. So it's 12 plus xy. And integrate under these regions here are. So typical we use this dA and you can write like this, right? That means be careful about these notations, right? So this notation is dA. And that means you're integrating under this region A. So what is this region A here? You can say, here, this is 12 plus xy. So if I want to integrate along the dx first, dy. So if you do the x first here, right? So if you do the x first, then you need to use the x limit here, right? So now I said dx, I can from 4 to 6. And then what is the y? Y is from 3 to 5 here. That's what it wants you to do here, okay? And then let's take a look at number 5 here. So let's say let the R is from the 1, 4 to 5, 9. Evaluate this limit to dA. So in here, I know I'm trying to find the volume under this function. And this is just like the function, this is just like a fixed height is equal to 2, right? So what is the length here? This is 3. What is the length here? This is 4, right? So I know this integration, I don't even need to carry out what is here. I know this is the 3 times 2 times 3 times 4 times 2. So this is 24. It's the volume of this rectangular box here, right? So this is the area, this is the base area, and this 2 is the what? This 2 is the height, right? So this is the height here. Okay, let's take a look at this one. I like those true or false questions here. So in here, okay, so is the integrate xy dA is equal to the x and the, so can you do like a separate like this, like means x dA and y dA? Can we do that? No. So this is what? This is a false here. Okay. And so how about this one's here? If I have a constant, can I take the constants out? Yes, this is true. Okay. So in here, the number C is very interesting. They say I'm integrating xy in this area R3. Okay. So in the R3, and then can I separate this one as I integrate the area in the R1 and R2? Can I do that? So R1 is 1 to 2, 6 to 7. R2 is 2 to 3, 7 to 8. R3 is 1, 3, 6, 8. Well, can I do that? Okay, so if you take a look here, right? So let's, okay, so let's take a look at the integration regions here, okay? So the first one, the R3 is 1 to 3, right? So this is 1, 2, 3, 1, 2, 3, 1, 2, 3, and 6 to 8, 1, 2, 3, 4, 5, 6, 7, 8, right? 6 to 8. So this is 6 and 8. So this is my what? This is the R3s, right? Okay. Now I'm doing a side-by-side comparisons here. This is 1, 2, 3. This is 1, 2, 3, 4, 5, 6, 7, 8, right? Okay, so now in here first, I'm taking a look at the R1. R1 is 1 to 2, 6 to 7. Okay, so this is 6, 7, 8. 1 to 2, 6 to 7. So this is what? This is my R1s, right? Okay, now my R2 is 2 to 3, 7 to 8. So it's 2 to 3, 7 to 8. So this is what? This is my R2. So are they have the same integration region? No, right? So that's why we say this is what? This is the, you know, so we say this is the false also. Okay, so this cannot be true here. Also, like in here, I cannot change it to the XY and the YYs here, right? So I cannot do that. Okay, so now let's take a look at problem number 9. Okay, so we have a very important theory. We call it the Fubini series. Okay, so Fubini series tell you if f is continuous, and in fact, you know, you said, hey, you are integrating over this rectangle agent, it's dAs, right? You can switch. So it doesn't matter, you integrate the x first or y first, as long as, you know, the f is continuous. So you can switch the x or y. Of course, you know, if you do the x first, then this has to match x, right? If you do y first, this has to match y's here. So it doesn't matter. So it's just like, you know, you need to be careful. Okay, so now let's take a look at these ones here. So when I try to do 1, 3, 2, 0, now take a look here. I'm doing what? I'm doing y. I'm taking the integration for y. What's that mean? That means x is a constant. So I'm doing here. So it's 1, 3. Okay, so I'm doing to y's, right? So x is constant. So what is the first term going to be to? It will be x squared, what? Y. Now what is the second term is going to be to? The 4y integrate will be what? 2y squared, right? Then you put a 0, 2, then you dx. So when you substitute the lower and the upper bound, so you will have here So you will have 2x squared plus 8, all right? So your y integrated out. Now you have dx. Now you do the integration for dx again. So this is 2/3 x cubed plus ax. Then you put your upper bound and the lower bound. And so this will be 100/3 here. Okay, so now let's take a look at this ones here, right? So this one's here, take a look at what I'm doing first. I'm doing x first. If you're doing x first, that means y is a constant, right? So this is 0, 2. So if you do x first, what it will give you? You will give 4x squared. Don't forget y is a constant, right? Then you plug in the limit to 0, 3. Then you still have a dy left here, right? So you plus the 3 times 9, 36. Okay, so you have a 36y dy. So this is from 0 to 2. And now you do the integration one more time, you will get 18y squared, 0 to the 2. So what is the answer here? It's 72 here. Okay, it's pretty straight, pretty easy, right? Okay, so now let's take a look at one more examples here. So it's find the volumes, right? Okay, so now your top curve, top surface is z equal to the sine x plus cosine y. Okay, so I know when they say find the volumes, right? That means you find all the volume under this curve along these regions, right? Okay, so I know when I mean to find the volume, what I mean? I mean, I'm trying to do the integrations, right? So I have the integration. This is the sine x plus cosine y. Okay, so let's try to write it. So in here we say it's dA, you integrate over this region, and this region is ours here. Okay, so now let's try to write it. Like I said, doesn't matter you want to integrate x first or y first, right? So you just need to match the, so I say let's do the dy first, right? So what is the y? I need to from 0 to what? Pi/3. And what is the x here? Is 0 to pi over what? Pi/4, right? So be careful, right? So if you do dy first, this one has to match the dy, right? Okay, so now when you do the integration of the y, so what is your x here? X is a constant. So this one will be y sine x. So what is the cosine y integration? Sine y. Okay, so now you input the upper bound and the lower bound, the dx. Now you need to use your unit circle. Hope everybody still remember what is a unit circle. So then anyway, so after you put it, it will be the pi/3 sine x plus the square root of the 3/2. And now you integrate the dx, right? Okay, so one more time. Sine integrator is a negative cosine, so it will be cosine. And then this is the square root of the 3/2, just the x. Now what is your limit? 0 and pi/4. Then you substitute this ones here. It will give you something like this. It's pi/2 times 2 the negative 2 minus the square root of the 2 plus the square root of the 3/4, or you put it into the calculator, will give you something very close to the 0.986. Okay, that's it. And then the last things here is we want to talk about is the average values here, right? So this is very similar like in the Calc 2, if you remember. Okay, so what is the average value for the functions here? Will just be the same thing. It will be minus a, and then you integrate from a to b, f of x dx, right? So that is what we say is the average values here. So if you kind of remember in the, in the calc 1 here, the calc 2 here, right? So if this is the AB here, right? So the average values here is kind of like you can find, you use this one divided by that, and then it's kind of like you can find somewhere here, okay? So then you will see the values there. Okay, so like in here, now the same things here, we can see here. Okay, so they tell you that here, this is 11th here, right? And then what is the average value of xy over r's here? Okay, so then you said the f of the average value, so what it will be? Hey, they already give you, so it's 11. And what is here? So the area, so this is the over, so in the calculus, right? This is over the length of this integration areas, right? So then here, this is the same, is the, instead of the length of the interval, I need to find the area. So this is the what? This is once, right? Okay, so this is, so the length of this ones here is 1. So what is the length of here is 2. So what is the areas here? So not the delta area. So what is the area for this R? So the area for the R is just 1 times 2, right? So it will be 2 here. So the average values here will be 11 over 2 here, okay? So that's the same things here, like the same way like what we did in the calculus 2 here. Okay, so now this we finished the first topic, and kind of the refresh your memory of the Riemann sum, and it's very similar like what we did in the calculus 2, the Riemann sum concept. Right now we expanded to the R3, and also in here we talk about, do the integration. In the calculus 2, we find the area. In the R3, we find the volumes, right? And then the Fubini theory tell you, if f is a continuous function, you can switch the dx dy. And of course, when you switch it, then the boundary you need to switch as well. Okay, that's it. So the next topic we're going to talk about is how about your integration region is not this nice anymore. It's not a rectangular anymore. Then how do we do it? Okay, looking forward to talk to you in our next video. Okay, bye.